By putting equation 10 and 11 in equation 9, we get d dt of kinetic energy plus r into dx upon dt bracket square plus d dt of potential energy is equal to f0 sin qt dx upon dt. Rearranging above equation, we get d dt of kinetic energy plus d dt of potential energy is equal to f0 sin qt dx upon dt minus r dx upon dt bracket square. But total energy is equal to kinetic energy plus potential energy. Therefore, we can write d dt of total energy is equal to d dt of kinetic energy plus d dt of potential energy. Now, we can write d dt of energy, total energy is equal to f0 sin qt dx upon dt minus r dx upon dt bracket square. Taking average energy over the period, we can write d dt of energy, that is average energy, is equal to average of f0 sin qt dx upon dt minus average of r into dx upon dt bracket square. Let us solve the first term of above equation, that is f0 sin qt in bracket dx upon dt. We know the displacement equation, that is x is equal to a sin qt minus delta. Differentiate above equation with respect to t, we get dx upon dt is equal to aq cos qt minus delta. Multiply both sides of above equation by f0 sin qt. We get f0 sin qt dx upon dt is equal to f0 aq sin qt cos qt minus delta. Using formula cos a minus b, we can write f0 sin qt dx upon dt is equal to f0 aq sin qt in bracket cos qt cos delta plus sin qt sin delta. f0 sin qt dx upon dt is equal to f0 aq sin qt cos delta plus f0 aq sin qt sin delta sin qt. f0 sin qt dx upon dt is equal to f0 aq sin qt cos delta plus f0 aq sin square qt sin delta. Now, taking average on both sides, we can write f0 sin qt dx upon dt is equal to f0 aq average of sin qt cos delta plus f0 aq average of sin square qt sin delta. But over a one complete cycle of oscillations, the average value of sin qt cos qt is equal to 0. Since 1 upon t integration from 0 to t sin qt cos qt dt is equal to 0 and average value of sin square qt is equal to 1/2. Since 1 upon t integration from 0 to t sin square qt dt is equal to half. So, we get f0 sin qt dx upon dt is equal to 1/2 f0 aq sin delta. From equation 8, f0 sin delta is equal to raq. Therefore, we can write average of f0 sin qt dx upon dt is equal to 1/2 ra square q square. This is equation 13. This equation gives the average rate of absorption of energy, that is power absorption by the oscillating body from applied force. Now, solve the term r dx upon dt bracket square. We know the displacement equation, x is equal to a sin qt minus delta. Differentiate above equation with respect to t, we get dx upon dt is equal to aq cos qt minus delta. Squaring both sides of above equation, we can write dx upon dt bracket square is equal to a square q square cos square qt minus delta. Multiplying both sides by r, we get r in bracket dx upon dt bracket square is equal to r a square q square cos square qt minus delta. Taking average on both sides, average of r in bracket dx upon dt bracket square is equal to r a square q square average of cos square qt minus delta. But over a one complete cycle of oscillation, the average value of cos square qt minus delta is equal to half. Since 1 upon t integration from 0 to t cos square qt minus delta dt is equal to half. Therefore, average value of r dx upon dt bracket square is equal to 1 half r a square q square. This is equation 14. This equation gives average rate of dissipation of energy, that is power dissipation, in overcoming the external damping force. Put equation 13 and 14 in equation 12, we get d dt of average energy E is equal to 1 half r a square q square minus 1 half r a square q square. That is, d dt of average energy E is equal to 0. This shows that average energy E is equal to constant. Thus, the average rate of absorption of energy is equal to the average rate of dissipation of energy. That is, the average energy over a cycle is constant. Thank you.